Hello, everyone. I'm really happy to open the sensing track today with you. So I'm Camille. I'm from SBQuantum. We are a small company based in Sherbrooke, Quebec, Canada. And today I'm really happy to present you diamond sensing for the future of exploration. So our vision at SBQuantum is providing high resolution, game-changing new data based on quantum sensing thanks to the solution we are developing. So this solution is combining diamond magnetometry with tailored algorithms. But before we dig into the applications of this solution, I want to say a few words about about our sensor. So our diamond micrometer, so I have it in my hand. So it's a room temperature sensor that combines scalar and vector measurements. So it's a magnetometer based on NV centers in diamonds. And so the interest that it has is that it also has no dead zone or heading errors. And it's a very compact sensor, as you can see. And the sensing volume is really small. It's of the order of the micrometer. As I said, so it's a quantum diamond magnetometer. So the quantum properties removes drift and also reduces calibration errors. And finally, this sensor has high dynamic range and tolerance to gradient, which makes it really versatile. So as you can see, so the sensitivity of our sensor, which is a vector sensitivity because it measures not only the scalar but the vector field, is below 250 picotesla per square root of Hertz. And the accuracy of the sensor is 1 nanotesla. So it's really, really precise because it's represent 1/50,000 the Earth field. But not only we are developing a sensor, but we want to go beyond the magnetometer as a commodity game. Magnetometers have been seen as a commodity for years, but we not only want to provide sensors, but we propose ML compensation algorithms and data analysis and interpretation. So ML compensation algorithms are really important because magnetic signals are everywhere, and it's really important to compensate the noise that the platform we integrate our sensor. So to do so, we use ML algorithms that we develop in-house, and it enables satellite deployment of our solution and with also different other applications. For example, there are applications for agriculture for high accuracy magnetic navigation. We also provide data analysis and interpretation for strategic minerals discovery. And for this application, we are looking at drone integration of our sensor. I will discuss the details just afterwards. So we are looking at three application domains, three principal domains here. So the first application is for navigation. So I will talk about it just afterwards, but it enables to refine the world magnetic model, which is the map of the Earth magnetic fields, and also for magnetic navigation. There are also applications for the defense sector with magnetic intelligence that I will not detail today. And finally, for the mining industry, this type of technology can bring a lot of value to mining companies for strategic minerals discovery, and I will also talk about it a little bit later. So first, let's discuss navigation. So why will this technology will make a difference for navigation? First, because magnetic navigation would be useful in GPS-deprived environments, and also because we need updates of the maps. So unlike geographic maps, the magnetic North Pole moves a lot through time. So you can see on the right panel a picture that represents that. So we need to have updates of this map at least every 5 years for them to stay accurate. And we are, at SBQuantum, we are part of an NGA MagQuest challenge, which goal is to refine the world magnetic model with quantum sensing. So on the left panel here, you can see the world magnetic model, which is so the map of the Earth field. And we are partnering with a company called Spire to launch our technology into space in 2025. So it's going to be next year. And we are, so as I said, we are developing ML algorithms to compensate for the noise of the platform, so for the satellite. And with this challenge, we have an opportunity of 20 years of data production. It gives us also the opportunity to test our sensor in world-leading facilities such as the NASA's Goddard Space Flight Center in Washington. The future is to have refined magnetic maps for GPS-free magnetic navigation, as I told earlier. So the interest of magnetic magnetic signals, magnetic fields here is that it's also passive signals, and it makes them also hard to jam or attack. And the measurement is also highly local. And so now it has no magnetic, navigation has no attackable infrastructure, and it also does not depend on weather, so it's a lot of different advantages for magnetic navigation. So now I want to deep dive on the mining applications of this technology. So we, as you know, we have net zero carbon emissions targets that we want to achieve, and to do so, it's really important to have electric vehicles, and these vehicles need batteries. And batteries will not be possible without minerals. So the minerals is a critical aspect in there, and different battery minerals, specifically such as nickel, lithium, rare earth metals, and also copper. And experts estimate that we will need 300 to 500 new mines to achieve the goals that we have set for net zero carbon emissions. But at the same time, exploiting a mine from the discovery of the minerals to the exploitation, commercial exploitation, is really long. It takes approximately 15 years. So that's why it's the time here is a critical aspect. We need to find better data. We need to have better data to find these mineral deposits. And magnetics is a technology that has been used for a long time. One of the first technology that has been used for mineral discovery. But at the same time, it has been limited in terms of data, which limits the interpretation that could come from the data. And also, it has noise limitation, like, so there has been a race for sensitivity, and sorry, and the data fusion is essential. So combining this technology with other techniques such as gravity or radiometrics makes it brings much more value for the end user. With SBQuantum technology, we are able to generate 8 times the maps to understand the geology in three dimensions. So the current industry solution is what I would call an Earth one-dimension X-ray. So it's only one layer of map. And what we are developing is a 3D MRI, if I could say it this way. So it's actually 8 times more maps, which gives much more information, especially specifically on the ground, and is really interesting for to know if there is an interesting zone for exploitation of minerals. We have at SB a multi-year agreement with the Geological Survey of Canada in Turner Bay. So we have been doing deploying our technology to the field in order to refine the features of our sensor. We also have done pilots. So, for example, a snowmobile survey in Glencoe, Raglan. So it's a mining site. Also to refine the features of our sensor. And finally, we have been testing our sensor in Natural Resources Canada, which is a world-leading facility in Ottawa. So now I want to show you how the maps looks like, what we were able to generate thanks to our technology. So on the left panel here, you can see a low-resolution map of the zone that we surveyed. And on the right, it's a high-resolution map that was available for this specific zone. On top of the low-resolution map, you can see the survey lines that the team was able to do with our technology. And so what we can see in this low-resolution map, so first, the blue zone, the blue circle here, represents a zone that was not really well defined, not defined at all in the low resolution map. And so we could see that the zone was of interest. And if we look at the high resolution map, actually we see a very good correlation of what we sensed compared to the map that was already available. Also, as you can see on the red circle here, so there was this yellow zone that was not really well defined, and we could see that for us this zone should have been more on the right side, so should have been longer, and it's also very well correlated with the high resolution map. So actually you see that the zone, the red zone is really well defined in the high resolution map. It also, so it gives us the opportunity to discover new mineral zones. So from the survey that we did, there is an example on the right of the maps that we were able to generate. So it's way more precise than the maps that were done before, and it enables to reveal unexposed high potential mineral units that could be used for and exploited for the mining industry. For this domain, our next step is to co-integrate our magnetic sensor with a gravimeter on a drone platform. And of course, the objective is to accelerate minerals discovery. Integrating our sensor on a drone will make the surveys way cheaper and way faster for the end users. We also want to provide a data portal, so the maps that we are generating, integrating into this portal in order to have, for the end user to be able to filter also on the specific aspects they want to look at, so the minerals or the different maps, because as I said, it generates an important number of maps. So this in order to make the end user life easier and to provide a full solution with our data portal. So this you see on the left panel our team. So everything this is made possible by our great team based in Sherbrooke, Quebec. If you are interested in our technology, I invite you to join us to deploy quantum magnetometry in Earth and space. There is my LinkedIn QR code here. If you want to connect, I will be glad to discuss with you. We actually are part of a Canadian delegation in Paris that's going to take place not next week, but the week after. So it's a great opportunity if you want to connect. If there are investors in the room, so we will have a seed round in this year, in the next month coming. So if you're interested in helping us deploy this technology, please let me know. Thank you, and I'm really happy to take your questions if you have any.
Hi, for the mineral discovery, do you plan to do that as a service, or do you plan to sell the equipment for the mining explorers?
Oh yeah, so actually it would be a service, and so we would have this surveys done, and then we would provide the data. So not only just selling the equipment, but really providing the full data interpretation and maps for the mining companies, yes.
For other applications, would you sell the equipment as well and have us deal with it?
So what applications are you looking at?
I can't really, we can take that offline.
Oh yeah, okay. Yeah, we'll be happy to discuss that, yeah.
So I have a question in the continuity of what have been said just before. What is the depth of what you can measure? I'm thinking more about oil and gas application.
Yeah, so it actually depends. We are able to have the gradients. So as I said, it's 8 times the maps. So for example, we are able to provide information on the dipping angles, for example, of minerals deposits. But yeah, I will be happy to discuss that further with you for the oil and gas specific application, because I know it's also very specific and not exactly the same as for the mining deposits.
So, thank you. This is Martin Dukowski from Aramco. Have you ever had a chance to see the basement in your measurements? So where the sedimentary basin ends and the magnetic rock below starts. Has that ever showed up on your maps?
So yeah, actually we are able to yeah, as I said, so we are able to know, for example, if we have a deposit of interest that is not like just below, and as for example some angle, we are able to say with our technology the angle, the deposit, where the deposit is, and which angle it has underground.
I was wondering about absolute accuracy of positioning, both today with current gravitational maps and then after you start to have the satellite system up and going. Have you done any forecasting on navigation based upon absolute accuracy of now and once the satellite system is up and going?
Oh yes, so actually, so for the world magnetic model, so it's part of the challenge. So the data that we are going to collect will be able to generate the world magnetic model. So it will be the model that we currently have. It's today, I think it's the 2020 version, and so it will be a new version of the world magnetic model. But yes, we are also looking at applications, for example, for agriculture. So we are looking at which accuracy we could provide for agriculture, for example, because it's. So actually, I can just show you the. So the accuracy of the sensor is around 1 nanotesla, and of course we are working to reduce this number, so down into the picoteslas. Oh no, I'm sorry, I cannot give you a specific number on that. I just come back to this. Yes.
Thank you. About the sensitivity, by the way, how do you compare to atomic vapor, for example, which are much more sensitive? What advantages do you see, especially for prospection?
So yeah, so compared to other technologies, so it's a vector magnetometer that we're developing. So it's so we are much more dimensions. So of course it's less sensitive, but we have the advantage of having not only the intensity of the field, but the field in each value, and which also can give us the gradient. So in terms of, so I would say that would be the biggest advantage of the diamond magnetometers in that way, the vector aspect, yes.
And the gradient, that's what.
Yes. The tensor, actually, yeah.
Thanks, Camille. I have a question about the magnetic maps you're actually doing there. I'm curious, do you know how they change over time? Because I don't have a feeling about that. I mean, is it something that you, as you said, just do one times in 5 years? And how is it actually locally? You know, is it really that you also need to do it once every 5 years locally, or is it even changing faster?
Oh, okay. Yeah, so actually for the world magnetic model, for like the Earth maps, yes, it's necessary to do it at least every 5 years, because otherwise it would not be it would not be accurate. So like you can see on the graph, like the North Pole is moving too fast. So it means that if we would keep the same map for 10 years, it would not be accurate enough. For smaller areas, so actually if you are looking at deposits, then you can if you collect the data and then you do an interpretation, then you are able to know which deposits are below. But this is less updates are less necessary there.
I have just another question. So if you want to do these type of maps, what you say, are you going to do that in satellites? I mean, how do you do these updates in the end? Or can you map essentially the parts from the satellite to the ground? Or how can I imagine that?
Mm-hmm. So for small zones, for mining sites, for surveys, it would be on the drone. But for the Earth maps that are less precise, that are more global maps, this will be done by satellite, yes.
One more question, please.
Sorry, you're mentioning drones. What's the power consumption of the magnetometer? Is it compatible with drones? Or,
yeah.
okay.
So, and actually we are not integrating only our solution, but also another technology, as I said, because it's really complementary. So we are partnering with another company that develops this type of sensor, and we co-integrate into a drone. So yes, it's actually compatible, and it's also the great advantage of having a compact sensor that makes it, of course, possible for drone integration.